Hello everyone, I'm Guangrui Qian. I'm from Department of Geosciences in Stony Brook University. Today, I'm very glad to have a topic about my work, the variable Cell NEB method, and I want to share some method in modeling crystal structure transformations. And you know, it is very common to have solid-solid phase transition and very high pressure. And we can generally divide these phase transitions into two different types. The first one, we call it reconstructive phase transition. And when we have it, sometimes it will change a lot and involving breaking and forming of the bonds. And you can see we can have diamond from graphite and very high pressure, but these two materials have totally different structures. And also, if the atoms moves a little bit and the strain was small as well, and we can call this kind of phase transition displacive transitions. And how we learn from these phase transitions, how the atoms move, how the cells transforms, we can start it from potential energy surface. And on potential energy surface, we can find minimal energy path, something like that. From the initial and final configurations, we can have several images there. And if we get the energy from these images, we can get the energy barrier. And the highest energy barrier, we call it saddle point. And this is also can call transition state from the transition state theory. But how can we get a minimal energy path? We call it MEP. We can have Nugent elastic bond method. In order to converge to the MEP, we need to keep the images on the surface, not slide into the initial or final point. So we need to set some artificial spring between the two images. And the force provided by the spring, we call it spring force. And also, the band will converge to the MEP by the perpendicular force provided by the potential force. And this method is proposed by Heckman and Johnson. But this method can only treat phase transitions without any cell transformation. So we proposed variable Cell NEB method. We study not only the surface and energy surface, but also the enthalpy. And the potential force can be divided by like this. And we then can coupling the cell lecture and the atoms. The NEB force can be described like this. And with this variable Cell NEB method, now we are ready to study reconstructive phase transitions. First, I would like to apply VC NEB method into a very common transformation, the B4 to B1. It is very common in group 4, 3, 5, and 2, 6 compounds. And people propose two different types of ways for this pathway. The first one we call it hexagonal. And you can see we have two different parameters to describe this unit cell. The first one is the angle gamma. Another one is the fractional coordinate u. And when we have a hexagonal structure, the angle doesn't change, but the atoms move up to this layer. And when we have a tetragonal structure, we first will have a transformation of the cell, then the displacement of the atoms. So what's the barrier would be like, and which one is preferred for compounds? We can study gallium nitride, nitrogen, B4 to B1 phase transition. After VC NEB calculations, we can have figures something like that. The first one is a tetragonal phase transition pathway. the degree changes and to 90 degrees. And the fractional coordinates changes a little slightly bit. And then we will get tetragonal structure. And the energy would be around 0.5. And the hexagonal structure pathway will be totally different. It's around about 0.4 EV per pair. And we can see that first, the coordinate parameters, fracture coordinate will change, and then we will have a deformation of the cell. And so from this result, we can say that from transition state theory, tetragonal phase transition pathway would be much preferred. And for B3 to B1 phase transition, what we can do? If you don't need any information about the pathway, just like the B4 to B1, people propose two different ways. But if I don't know any information about it, I can only just left the method to VCNEB. After calculation, we can say that if we start from the structure A and then we want final D, we can get two different structures as well, the structure B and structure C. But if you learn it carefully, we can see that the structure A and the structure C have the same space group, but in different shape. And they all have the same phase transition pathway. And they will have the intermediate IMM2 space group. So VCNEB method is also powerful for starting phase transition if you don't know anything about it. Just let it do. Sorry. And also, the carbon system is a very complicated one. VCNEB can also treat it very easily. We proposed BCT carbon in 2010, and we started to learn the pathways on it. After the VCNEB calculation, we can find the mechanism of the phase transition. First, the atoms on the graphite layer will move a little bit, and then buckling. And then they will bonding and to form the square cycle or the 8-atom cycle. And if the atoms move in different sides of the layer, it will form the M carbon, another one. And this mechanism also can be confirmed by TPS method. And also VCNEB method, another power way is to find the metastable structures. These metastable structures sometimes are very important. And here we can find the hexagonal structure on the path at 14 gigapar. And this is also confirmed by others on the energy surface, describing with the fractional coordinate and the angle gamma. We have the same results. It is powerful. And now I would like to give a conclusion here. I proposed a variable Cell NEB method for starting solid-solid phase transition, especially reconstructive phase transition. And we imply VCNEB method in many systems. It's successful. And also, the VCNEB method is powerful to predict metastable structures on the pathway. And I will show you this point, maybe in the near future. And finally, I would like to thank these people. They help me a lot. And thank you all.